All right, so thank you everyone for joining. This session is titled Enable Agentic AI at Scale in the Enterprise with NVIDIA and IBM. My name is Joe Dain. I work in the Storage CTO Office at IBM. Also joined here by Jacob Liberman, who is the Director of Product Management at NVIDIA. And we have a very exciting agenda. We're very excited to talk about this today. We're going to talk about a problem statement of some of the challenges that enterprises are facing, bringing their data ready for agentic AI. We'll then talk about IBM content-aware storage. Jacob will talk about the NVIDIA AI data platform and some agentic AI use cases. And then we're going to tie it all together with our Fusion AI data platform. In order to be effective and relevant in today's modern AI enterprise, organizations need to enable agentic AI in AI applications. But in order to do so, they need to be able to bring their data to the applications. If you just take an off-the-shelf model and use that in your application, even though that data has been trained on, for example, all of the data available on the internet, it doesn't have the domain knowledge of your enterprise. And so what ends up happening is that model will hallucinate and generate answers that aren't accurate for your enterprise. And this is because they don't have the relevant data from the enterprise at all. Only 1% of enterprise data is actually used today in off-the-shelf models. So typically, a process called retrieval augmented generation, or RAG, is introduced to address this problem. In this example, without RAG, if you ask a question to an LLM, that question is directly sent to the LLM and it's going to generate an answer, and that's where the hallucination can take place. But with RAG, instead, once that question is asked, that question is sent to an internal retrieval system that has documents from your enterprise. The top results from that are then added to your original question and then sent as a prompt to your LLM. And now when the LLM answers the questions, it can do so grounded in the truth of your domain data. This allows you to have a higher level of trust, and you can actually trace the data back to the original sources and have auditability for how your responses were generated. But there's some serious challenges that we see customers facing time and time again when trying to implement these RAG solutions at scale. One of the most typical problems is that enterprises have a lot of existing enterprise data, and they typically either migrate it to a new platform to take use of it for agentic AI, or they make a copy of it. Once they make a copy of it, they lose track of the changes, and it causes a lot of overhead. And so once they do that, you don't know what data has changed. And once you don't know what data has changed, it's very difficult to keep up with it. Other thing that we see is that the security and access controls get messed up. So imagine that I have a finance department that has some data sitting on a data store, and I make a copy of this data because I want to use it in a Gen AI application. Oftentimes what we see is once that happens, you lose the existing access controls, and so you're effectively leaking data. So now as somebody comes into the end chatbot or application and asks a question, they can get access to that financial data that was previously locked down in your original data source. And so we've actually seen in many cases there will be lots of pilot projects for these applications that take place, and then they go through an audit or a security audit to go into production. And these projects actually get shut down entirely because they haven't addressed this. And so because they don't understand how to control the access and make sure that the data is still secure, the projects just never make it into production. It's also very complex. There's multiple technologies that you need to integrate in order to make a RAG solution work. And you really want your data scientists focusing on building higher level applications versus being down in the plumbing, trying to wrangle your data and get your data ready for use by AI applications. One of the other things that we run into is that when you make a copy of the data, you don't know when the data has changed. And so oftentimes applications in enterprises, once a week, they will take that data and make a copy of it again and re-ingest it again. When they do that, it creates a lot of unnecessary overhead, and there's a staleness of that data because the answers that they're answering at their end application could be a week behind. Since there may have been changes in the original data source, and they're just not reflected in time. And so when you combine these all together, it's actually very difficult to put RAG in these applications into production at scale. So to take a closer look at this, in this diagram you see an AI factory, where the AI factory is responsible for running inferencing applications, doing model training, fine-tuning, things like that. and then we have that connected through high-speed network to a storage device. And now let's say I want to prepare the data for use with an agentic AI application. In this case, I have a 10 terabyte multimodal data set. Multimodal refers to different types of content like tables, charts, text, audio, video, etc. The first thing that I have to do is take this 10 terabytes and copy it over the network to my AI factory. After I do that, I have to pass it through a RAG ingest pipeline. And this RAG ingest pipeline running on the AI factory is going to be responsible for preparing this data for use with your agentic AI applications. And this process is going to generate over 857 billion tokens from the AI factory. And that's a tremendous amount of overhead that puts a burden on that. As part of this process, we're going to take the data, we're going to parse it and chunk it, and then create vector embeddings, or a higher dimensional representation of that data as well. And those chunks and those embeddings then have to be sent back across the network, where they're ultimately stored into a vector database. And you can see in this example, the overhead, it's actually over 23 terabytes of chunks and embeddings that we have to create just to make this data ready for RAG. And so if you combine this all, now that 10 terabytes of data, we've had to create 33 terabytes of network overhead and generate over 857 billion tokens on our AI factory. So you look at this problem and you think, well, what if there's a better way to do this? What if we could eliminate all of that overhead on the AI factory and all of the overhead from the network? If we can take that processing and offload it into the storage and add GPUs into the storage and run the RAG ingest pipeline in the storage, now as the data comes into the environment, rather than having to send it across and do all that processing and bring it back, we can just process it in place and leave the AI factory for use for higher level applications that bring more value to your organization. But there's more to it. So typically, what I mentioned is that organizations don't know what data has changed. But if we have the ability to detect what data has changed, we no longer have to process that 10 terabytes over and over again. In this case, let's say that there's a 10% change rate and there's only 1 terabyte of data that's changed. If we can detect that and only process that, we can eliminate the need to reprocess 772 billion tokens. We can get a 10x efficiency, and we can free the burden of the AI factory from having to do this entirely. And so this is behind some of the motivations of why content-aware storage is coming about. Another part of this is if you look at unstructured data, it's really, really messy. For example, you can have scanned documents, and these scanned documents, there's quite a variety of them. People can write annotations in hand, and they're handwritten on top of that. There's multiple types of tables embedded in unstructured documents, also types of charts and graphics. And there's such a variety that you have to understand how to process. And on top of that, there's various technologies and tools that you have to stitch together to make this all work. So rather than being down in the plumbing and having your data scientists wrangle with this data and make this data available for Gen AI applications, why not offload this into the storage and allow them to build their applications instead? And so that's the motivation behind content-aware storage. And what we see is that historically with storage, there's a new protocol that comes out about every 10 years. So we started with block storage, and then we had the need for file storage. And then object storage came about. With object storage, now you have the ability to have rich metadata associated with the original data, solving a new set of use cases. And what we see is that with content-aware storage, we're now going beyond just a passive supplier of bits and bytes to actually being able to process that data and make it available for use with Gen AI applications in place. So as the data is coming in, we can parse it and chunk it and create the vector embeddings for it, and then present modern APIs that can be consumed by Gen AI applications, such as a semantic search API. And really, we're at the front of this. This is the beginning of a journey, and we see this evolving quite a bit over the next couple of years, and the amount of capabilities that are going to be offloaded into storage is only going to grow. And so what we've built is a Fusion content-aware storage service. And the idea behind this is that if I have existing enterprise data, we have customers that have hundreds of petabytes of data, for example, all the way down to terabytes to low petabytes. That existing enterprise data, they want to make it available for use with their Gen AI applications. But they don't want to have to make multiple copies of it, and they don't want to have to migrate it all at once. So what we have the ability to do is to overlay this technology onto the existing data and then process it through the RAG pipeline. We use Nemo Retriever to do that. It does multimodal extraction from text, tables, charts, infographics, and we're adding audio and video, which Jacob will show in a minute. And then as that data is being processed, it's made available for your Gen AI applications and your Agentic AI applications there. So one of the things that we do is that we worked with our IBM research team to preserve the existing access controls in this. So if you have file access controls set on your original data source, that example from the financial institution, those financial documents, as we ingest this content through the agent and through that and make it available to the agent, we preserve those access controls. So you're no longer leaking data, and there's a single source of truth for who controls the access. So if the access is changed here, it's immediately and automatically reflected through your chatbot. So you don't leak any data and you don't have any security holes. The other thing that we do is this incremental processing, where we can detect when the data is changed and only process that changed data, providing a freshness of the data and much higher levels of efficiency, because we don't have to do this batch process anymore, where we once a week re-ingest all the data and have a staleness of that content. Okay, and with that, I'll turn it over to Jacob to talk more about the AI data platform.
Okay, can y'all hear me okay? Yeah, okay, good. Yeah, thanks, Joe. So my name's Jacob Liberman. I'm a product manager at NVIDIA, and I'm very grateful to be here with all of you today. Like many of the people in this room, IBM has had a huge impact on my career. Even though I actually only worked for IBM for 2 weeks, it's touched my career at many different points that I'm going to talk about in my session later today. So please join me there. But yeah, this is Joe, I really love the way you broke down the problem statement and how CAS address many of those problems. I think it's obvious to a lot of people that it's inefficient to move the data back and forth and constantly re-index it. But you did such a good job of articulating that every time you move the data, you're increasing the attack surface on the data, and it becomes a security threat. So a typical enterprise, by our analysis, has about 13 copies of the same data floating around. Many of those will become shadow assets that are ungoverned, and they become disconnected from the source of truth documents. So by operating on the data in place, you can minimize the proliferation of those shadow assets and keep the data visible and governed. It's no longer a dark source of data, let's say. So, and CAS is providing the critical piece that enforces that. But zooming out a bit, we're here to talk about AI agents, and the thing I'd like to impress on everyone, and something that we all know, but maybe we forgot, is that data is still king. There's all this exuberance around agents and their capabilities, and they can write poetry and make videos and do all this stuff. But at the end of the day, every consequential AI workload depends on access to secure, accurate, high-quality data. So whether you're fine-tuning, you're training a foundation model, whether you're doing RAG, all of it depends on having access to high-quality, secure data. And that's also true of AI agents. So in recognition of this trend, and IBM's really one of the front runners and leaders in this area, but in recognition of this trend, NVIDIA has created a reference design called an AI data platform to create a new class of GPU accelerated storage. And for the reasons Joe explained, it's more secure, it's more scalable, it's more efficient to prepare the data for AI agents in place. And you really need GPUs to do that at scale. Not surprisingly, right? We believe GPUs are the answer for the question there. So our reference design includes our GPUs, our networking, and our NVIDIA AI enterprise software. Now, I'll go a little bit deeper into the trend here and how this is really a natural evolution, maybe an example of storage just kind of moving up the AI food chain. So I remember when I put a storage scale 6,000 here, but I remember initially when I started working with storage, 25 years ago or whatever it was, you had a JBOD that you would connect through some kind of interface, and on the server, you would put out the file system, rate up the disks, set up your data protection scheme, maybe a cron job to copy the data over. But eventually, the CPUs migrated into the storage. And at that point, the storage CPUs were responsible for the data serving, the data protection, and the protocols. And at a certain point, as CPUs became more powerful, maybe after like the i686, we got to multi-core, that spare CPU capacity could be productively applied to doing operations on the data in place. So in your storage, you started seeing things like deduplication, compression, etc. These are beyond the basic capabilities of protecting and serving the data. So you can really view CAS and what we're talking about today as a logical evolution of this trend that started 20 years ago. Now that generative AI has become a dominant workload in the enterprise, it's no surprise that preparing the data for generative AI occupies a lot of our time. And the storage is moving back to the center of this whole discussion because we're realizing that's really where those data preparation options or actions should happen, including things like collecting the data, extracting the text, creating the embeddings, and indexing into a vector database for efficient search. And in the same way that the spare CPU capacity in a CPU-based server could be used to operate on the data, there's ample spare GPU capacity generally that can be used to provide another set of AI data services on top of that data. It makes sense that things like PII redaction, document sensitivity analysis, semantic deduplication. Semantic deduplication is you don't duplicate identical or deduplicate identical documents, you deduplicate them if they have identical meanings. For example, if you have 9 hours of footage of an empty road, you probably don't need to retain all of that, you can deduplicate a lot of it. So these AI data services are actually AI agents running in the storage, looking into your documents, understanding their contents, they're content aware, and making decisions about how to, adding, let's say, additional services on top of that. And for storage, this is really a tremendous opportunity for storage vendors like IBM who have a research department and all this rich capability, because they can actually, having access to the data and having the GPU capacity opens the door for a whole world of new innovations and value that they can provide to their customers. So what we're doing now, preparing data for RAG and fine-tuning, is really just the first step. And we have an exciting roadmap, collaborating with IBM Research, of features that will be upcoming that will be more in this area. So does that make sense, guys? The introduction of a GPU moves the storage up the food chain, and now it's become a critical part of the AI infrastructure. And IBM CAS is really a leading example and a first example of that. So this is the obligatory, picture of a GPU. But this is obviously tied to our Blackwell GPU launch. Our Blackwell GPUs are our latest generation, and they're our most efficient GPUs that we've built to date. This particular GPU is a great fit for CAS because it is a PCIe GPU, and it runs at 600 watts, but it has more than twice the capability of the prior generation PCIe GPU. So essentially, we had a pipeline that would take 4 GPUs, before. Now you could run the same pipeline on 1 or 2 of these and get better performance. And that's really a key for the storage market, because it is a cost competitive market. It is cost constrained, it's space constrained, it's power constrained. So you want to make sure that you're right sizing your GPU investment for those storage operations. This is something Joe didn't mention, but if you're doing all this stuff in the factory, if you're doing the data prep in your infra for training and inference, that's kind of a misallocation of resources, because those GPUs have been sized and scaled with regular token economics. You want those applied to doing training and inference and productive work. By operating on the storage in place, you have another benefit where you can scale your factory with your agents, and you can scale your AI data platform with the data. So as the data grows, you can use these more appropriate, maybe lower cost GPUs and scale out. And as the number of agents grow, you scale out, let's say, the higher value GPUs for those workloads. And then, of course, we have servers that hold these GPUs. Okay, so now we'll go into some of the agentic AI use cases that this enables. And, so this is actually what I just mentioned. I forgot I had this slide. But a typical AI factory is here on the left. And the notable difference between, another notable difference between the factory and the data platform is the inclusion of an east-west an east-west fabric. When you're training and you're checkpointing large-scale training jobs, you need an additional network that you can use to synchronize the data across the hosts. This is important to work training jobs efficiently and also to make sure that they're fault tolerant. This is not needed in the platform. So applying that work here is another example of how these nodes might be over-provisioned for that workload. So you can imagine that you have a factory, you're running hundreds of agents, thousands of agents, chatbots. We have a factory we deployed inside NVIDIA where we're doing something like this. It's called Astra. And they're all hitting this same centralized storage that's protected in the way that Joe described. It doesn't make sense for all of these hundreds of chatbots to have their own shadow copies of the same centralized local data. So we're reducing data sprawl. We're sizing the GPUs for the data velocity. The velocity is the growth and the rate of change together. We're preparing the data in the data path, which reduces update latency. You're not mounting the data over here and updating it. You're preparing it in the data path. And then you can also, and another security benefit aside from the data recency and data sprawl Joe mentioned is that if you're doing the data preparation over here, you're doing it in the in the user plane. Now your users are in the same tenant, the same namespace as the data. Let's say I have a picture of Joe's driver's license somewhere in this data, and I move it over to the factory. Potentially anyone in that tenant can get access to that picture of his driver's license. So it's really much better for him if I redact that here before it's ever shipped over here to the tenant. And then we also get to reserve these GPUs for tenant workloads. So I'll show 2 of the use cases we're rolling out together jointly. These are based on NVIDIA blueprints. So NVIDIA blueprints are reference architectures implemented in code, and they're meant to be taken and adapted. So we give you a fully worked example, and then you take it and kind of tool it into your environment. And we have one called Video Search and Summarization Agent and one called the IQ Deep Research Agent. You can think of these as a general class of problems. One is video intelligence, the other one is document intelligence. And this is the one we started with. So I'll just show both of these briefly. Now, both of these blueprints are built on top of our RAG blueprint. Joe talked extensively about RAG. This is a high-level view of our RAG pipeline based on our Nemotron and Nemo models and our Nemo retriever models and our NIM microservices. And our pipeline supports text, audio, graphics, and images. You can create and search multiple collections with custom metadata. You can use a VLM in the response, so like you can send it a picture and say, what's this a picture of, and it will tell you. You can do hybrid, sparse, and dense search, and then re-rank the answers based on their groundedness and relevancy. And then we also have guardrails. This blueprint is the common foundation for the document intelligence and the video intelligence workloads. So this is a video of the video search and summarization agent, and then I'll show the architecture. We don't have sound, but there is a piano playing. So what's happening here is this is actually a real-time feed of a sporting event, and this is actually synthetic data we generated. But as the data is coming in, it's being instantly indexed and processed so you can derive insight from it. This is an overhead view from a drone of a traffic incident. And then we can also have stationary cameras or moving cameras, and real-time worker safety is a dominant use case for this, et cetera, et cetera. So we have many applications of the same technology, but the important point here is that whether it's archival data or streaming video data, because we're indexing it in real time in the storage and securely, we're able to get the insights from the data in real time and at large volumes and large scale. So we have not implemented this use case yet, but this is next on our roadmap. So yeah, let's go to the, or can I do that? Yep, so high level view, this is more or less the same ingestion pipeline that you saw in the RAG blueprint, except we have a computer vision pipeline. Before Gen AI, computer vision was the dominant use case for GPUs, so we have some experience there. And we can ingest the video archives or the camera streams, process them with a VLM, and we put them into a vector database for semantic search. And we also use a graph database to add temporal and spatial locality. So you can have high acuity in terms of the sequence of events that happen, which semantic search can sometimes lose. Yeah, sorry, it's me. This is another video then of our research agent, and this is based on our reasoning NIM. And so what this allows you to do is once you've sucked all your enterprise documents into your CAS system, you can chat with a research agent. It's a deep researcher that will look into your private data, research, and answer the questions. So this is a little hard to see, but it will expand. But it's a typical kind of interface. You click Begin Reasoning, and you give it a report topic, and then you can actually define the structure. You can give it an example or just describe the structure that you want it to generate the report in. There's a lot of standard structures that people have to generate over and over. The way this works is that your files are ingested into your CAS. The agent can run in your factory. So you have GPUs out in the factory, or this could be a remote endpoint, like some commercial endpoint. You ask it the question. The agent then creates a plan for generating the report, mines your private data, brings in the private data to generate the report, uses an LM as a judge to reflect on whether the report is well-formed and accurate. If it's not, it might refer to secondary sources like a web search or send it back through with a rewritten prompt that the agent rewrites until you have a report that matches your specifications. Yeah, so that's it with the use cases. And I'm going to tee up his next thing here, but what you could see is that the data processing happened in the CAS, in the AI data platform, and the agents using the data ran in the factory. But that doesn't always have to be the case. All right, thank you.
Okay, so what we're going to talk about next is how we're pulling this all together within our IBM Fusion platform. And what we've done is we've taken the content-aware storage component that we previously discussed, and we package this into our Fusion HCI appliance in particular. And so this gives us the ability to, seamlessly connect to existing enterprise data, eliminate that copy data sprawl, preserve the existing access controls, and then with that, allow you to use that data to extract the semantic meaning from the text tables and multimodal content, whether it be infographics, the video that's coming soon, and other types of capabilities. The AI data platform that reference architecture that Jacob mentioned with the Blackwell GPUs, we've integrated and optimized that into the Fusion HCI platform as well. So we get a lower TCO, better performance, and we're doing quite a bit of engineering work to be able to optimize not only content-aware storage, but other types of workloads on this as well. So for example, if you have previously running some L40Ss with content-aware storage, you can reduce that and use these Blackwell GPUs instead and get higher performance. Along with this, one of the things that we've been working on is the sizing calculator, so that if I know what my SLA is for how much data I want to ingest, I can size the platform accordingly, and so I can have predictable ingest performance and query performance. Then the other thing that we're doing, we talked a lot about the AI factory and integration with the AI data platform. There's two ways to do this. One is you can take the Fusion HCI appliance and use it as an AI data platform and attach it to a bigger AI factory. And this is going to offload all that data preparation and data processing into the data platform to free up your resources in your AI factory. But we do have a set of clients that want to get started with Agentic AI right away, and they might not necessarily be ready for a big AI factory right now. So the other thing that we've done is taken the models associated with running Agentic AI, such as a Nemotron reasoning model, Llama LLM, and we package that into this Fusion HCI appliance in a way that we have it sized as well. So you can allocate a portion of this for data ingest with content-aware storage. You can also allocate a portion of this to run Agentic AI applications. And we'll take a closer look at what that is and what we prepared. So Fusion HCI is introducing a new GPU node. We call it the G04 GPU node. And with this GPU node, we can scale the number of Blackwell GPUs in it. Once we have those GPUs in it, we can then allocate basically the workload for the content-aware storage. We can scale it up as you need to. So we have small, medium, and large. If I have a small, I have up to 4 Blackwell GPUs, and then I can scale the amount of data that I can ingest per day based on that GPU workload. I can also then, if I want to use the optional Agentic AI piece, we've engineered it and optimized it so that you can run the Nemotron reasoning model and a Llama 3.3 model as well. So then you can scale this out moving forward if I want to get higher levels of ingest, or I want to run more agentic applications and I want to get grow my environment in that aspect. I can simply go to these different sizes, and these sizes are not fixed. These are meant as a starting guide. So we have the small, medium, large that allows you to go into the ordering system, use this small configuration to get started right away. Or you can go to one of the other sizes, but you can also customize it. So this is making it easy to get started on your Agentic AI journey, whether that's just preparing the data for use with AI agents or actually running the agents all in one inside of the platform as well.
So guys, just one closing remark. What I love about this vision, Joe really said the operative word there, which is that they're making it easy. This problem of preparing data for AI and keeping it secure is a hard problem. And with HCI, they're making that hard problem easy, not just in the t-shirt sizes of how you can acquire it and size it for your data, but the whole process. Finding the data, securing the data, preparing the data, and then by hyper-converging and bundling the agent in with the storage, it gives enterprises a nice on-ramp into Gen AI that are maybe just getting started. And then probably the factory will grow around that as the number of agents and use cases expand. So if you take anything away from this, I think that that's really the key point here, is that IBM's found a way to make this very hard problem easy for their enterprise customers.
Great. Any questions? Yeah, so the question is, if we want to start with text retriever and we want to add video, how does that work in terms of resource allocation?
So like we mentioned, we've not implemented that yet, but in general, the blueprints are meant to be composable. And in reality, the video search and summarization blueprint does have an OCR capability to process text, like license plates, things like that. Similarly, the retriever blueprint has a capability to process video, but both are optimized for their own type of data. So what we foresee for our customers, it's much better to have a highly optimized document intelligence pipeline and a highly optimized video pipeline than one that's really good at one, but not so good at the other. And so we've actually built an integration so that you could deploy these things alongside each other and size them separately, grow them independently. And they have a way, it's basically a prompt injection technique to share data back and forth. And what that allows you to do is take your private enterprise data and use it as part of the analysis of the video. That's a fundamentally new capability. So we're going to bring that out soon. So the users have basically two options. You can deploy your document intelligence alongside the video intelligence pipeline and connect them, or you can, if the majority of your work is on one modality and not the other, either of these will actually work with both modalities.
And to add to that, Frank, what we're doing thus far is the first approach, where we have both running inside of Fusion, leveraging kind of the inherent architecture of Fusion to be able to do that. So we have that. We worked on that with research and the CTO office, and it's with development right now to finalize that, and that's in the roadmap, I think, for it. We would use. Go ahead. Okay, we would use MIG, multiple instance GPU, and so you can allocate portions of the GPUs for the workload and size it accordingly, so that you have guaranteed SLAs for the different pipelines that you're running.
Yeah, and this brings out another important point, is that even though we've created a reference design, IBM's taken it and really optimized it for their portfolio and their technology, their users, and their use cases. So we have some kind of general recommendations. Generally, you can use MIG to subdivide the resources. You could also use something like kserve or to trigger serverless functions into the same pool of GPUs and do it in a more, say, dynamic way. There's a lot of optionality, but then it comes down to optimizing the specific implementation, which is what they're doing with the research group.
Right. And the other way we're using MIG is to run multiple parallel instances of the ingest pipelines on the same GPU to get higher parallelism and higher throughput and reduce the TCO. Any other questions? Okay, so the question is related to ACLs on the file system, and if that is pushed through the pipeline to the end application. And the answer is yes. There's two levels that you can set. One is at the domain level, so you can go in and at the search domain, and at the search domain you can add individual users or entities that have access to that search domain. But you can also enable file level granularity, whereby as the ACLs are changed on the file system in real time, as those queries come in, is actually using the latest and greatest ACLs on the file system to make sure that nothing is leaked up to the end applications. That's one of the pieces that we worked on with research. Yeah, correct. All right. Thank you very much for your time, and have a great day.